Okay, so suppose if you had a tube like this, so instead of the tube being straight in equal cross section, or uniform cross section, sometimes you will see some tubes like this. This is mainly done to do the measurement of the fluid flow. Okay, so if I want to do the measurement in a fluid, how much fluid is flowing through, right? So, say for example, in some places, they have started fixing this water meters. So it means depending upon, instead of paying a constant bill for, every month or every year, what they are in future, what they will do is they will fix a water meter, just like an electric meter, right? They will fix a water meter, which means depending upon how much water you are consuming or how much water you are taking in, you have to pay the bill for the corporation, right? So that kind of applications everywhere, you will get. Particularly in industry, you have to keep on measuring how much fluid is flowing, right? For example, in a petrol bunk, what are you doing? We are actually measuring how much fluid is flowing, right? Of course, you have much more sophisticated equipments, but then the equipment which we are going to talk about is called,
Venturimeter.
yeah. So the principle in this is you have a U-tube connected between two different areas. Okay, so this cross-section area is much larger and this cross-section area is much smaller. Let's call this as A and B. As I told you somewhere else, there is something called manometer liquid. And then let's say this is a liquid, which is, the manometer liquid is initially, let's say this is the red one. Okay. So as the liquid starts flowing, right, as I told you, it can be water, it can be some other liquids, right? So as the liquid starts flowing through this, can anyone guess what's going to happen to this liquid here? Is it going to remain like this, or is it going to, go up here or go up here? What do you think? What did we study in the last class? So the pressure here, when the area is bigger, the pressure will be, and the area is bigger, the velocity is slower, right?
Slow.
So when the velocity is lower, pressure will be
More.
higher.
Less.
Yeah. So here the area is smaller, which means the velocity is faster, right? So it will be going faster. When the velocity is higher, the pressure is lower. Okay, I showed you the paper experiment. So I hope you tried it yourself. So that means the pressure here will be lower, which means the manometer liquid will rise or will it get pushed downwards? What do you think? It will rise, right? Here the pressure is higher, here the pressure is lower, which means what will happen is here the pressure is higher, whereas here the pressure is lower. So you need to understand the very reason why I'm showing two different colors is one is the liquid which you are measuring, and the other one is the manometer liquid, which is usually mercury. So the red one is the mercury. The blue one can be water, or it can be some other liquid like petrol or something like that. So this height is your H. You know that the pressure difference between this and this is nothing but your rho GH, right? If you don't remember that, we studied something called U-tube manometer. So U-tube manometer, we studied two different variants. One is open to the atmosphere, the other one is two different pressures, which means the rho GH which you see is nothing but the pressure differential. That's why it's called differential manometer. Okay. So that means this is acting like a U-tube pressure manometer or differential manometer. Okay. So to find the difference between these two pressures. Of course, I showed the A here. Okay, maybe the tube I can show it over here, A and B. So what is the simple principle which you have been using? energy at 1 or energy at A should be equal to energy at B. Okay. So you see the height is same, which means the potential energy does not change, right? In the derivation, we studied a tube like this, which means the height is different. Okay, that's why we brought in mgh1, mgh2, and then rho gh1, rho gh2 in the Bernoullis here. Here, since the height is same, right, we don't worry about the potential energy. So instead, what we do is, one more thing I forgot to tell you here is this density of this liquid, we take it as rho. Density of this manometer liquid, we take it as rho n. So the thing you have to be careful here is there are two different liquids involved. Okay, it's not just one liquid. So the energy, the total energy at this place can be written as pressure at A plus half rho V square. Pressure at this point can be written as PB plus half rho VB square. Why we didn't write the rho GH? Because even if I write rho GH here and rho GH, the height is same, rho is same, which means these two will cancel. So that means I don't care about the rho GH. If you want, you can write one more step. And what are we interested in? We are interested in finding the velocity of the liquid. Okay, how quickly the velocity is flowing. Sorry, the liquid is flowing. So you can do the math. Okay, as I told you always, you can for derivation, in term 2, you have the derivations in your school exams. So you should be thorough with the derivations. You have to practice it. Okay, as I always say, brain, paper, pen. Okay, if you keep staring at the handbook or a textbook, you are not going to learn physics. Okay, you have to take a pen in your hand or to take a notebook and start writing the derivations. Unless otherwise you do that, you are not going to learn physics. Okay, that's what we have done here. So if you are doing a numerical, I would not recommend you to remember this final formula. Okay, so that looks very complicated. What you have to solve, you are supposed to remember is this basic principle: energy A is equal to energy B. Write down this and then substitute the numbers here. Whatever numbers are given, substitute, and you will be able to solve for the EB. Okay. Only for your derivations, you need to derive that final formula. Suppose if I say PA minus PB, I said pressure here is bigger, pressure here is lower at P. So that means I'm going to write as PA minus PB. And from differential manometer concepts, I already know that this differential pressure is nothing but rho GH, which means in this place I can write rho GH, and this will go to the other side. Half rho is same, PB square minus VA square. So you know that there is something called equation of continuity, right? Anybody remember what is equation of continuity?
Is equal to constant.
Say that again.
So AB is equal to constant.
AB is equal to constant. Very good. Okay. So A B is equal to constant. Okay. So Ashwin, now you're turning your pages. At least before coming to the class, you should go through what we have done the previous class. Otherwise, it's going to be very difficult. So area at A, velocity at A should be equal to area at B, velocity at B. So why would I do that? Because measuring the area is easy. Okay, determining the area is very easy because I can take a simple scale or a vernier and I can calculate the diameter of the pipe. Once I know the diameter of the pipe, I can calculate the area. Okay, so measuring the area is much easier. So if I don't know the velocity here, let's see what is that we are interested in. We're interested in velocity at A. Okay, so what I can do is I can replace VA by VB. So I'm going to take VA, I'm going to take it out commonly. So half rho VA square is equal to VB by VA the whole square minus 1. Because I'm taking VA square outside, okay, which means I need to divide this. Why would I do that? Because if I want VB by VA, I can simply write as AA by AB. AA by AB whole square. Of course, this I told you based on the manometer, differential manometer concepts, you can simply write as rho GH. However, you have to be very careful, as I told you at the beginning. This is rho of the manometer liquid. So this rho is different, this rho is different. If you make a mistake here, everything will go wrong. So that means you should understand this. This is manometer liquid, which is mercury. Okay, so this rho is the liquid in the pipe. To be measured. So as I told you, measuring the area is very easy because you can take a scale and you can find the diameter or radius and then you can find the area. So measuring this is easy. Density of the liquid should be known for a given liquid. For example, water means 1000 kg per meter cube. Petrol or diesel or some other oil means I know the standard values, right? So I know these things. So these things are also known from this experiment, which means I can calculate the dA. Okay. So you see, as I told you, there is no need for you to remember this equation, which looks very complicated. Okay. So as I always say, you should remember the principle, underlying principle. So if you don't understand this, there is no point in remembering this one. Okay, that's totally waste. So this equipment is what is called Venturimeter. Venturimeter. Meter refers to measurement. Okay, Venturi refers to shapes like this. Comes down like this and then goes back. So anything which is of this shape is called Venturi. Any questions? Very simple derivation. Absolutely nothing difficult here if you understand the basics. Okay. Can I change the screen? Can I move on? So the later topics, this one, let's see. These two things, I think, sometimes they ask you in the numerical, but it's not given in your hand, given in your textbook. Okay, maybe I can quickly go through it very quickly, so that again the concepts are exactly the same. Only thing you should know how to apply it in a situation. So this kind of arrangement is called Pitot Tube. So what it does is it's a very simple arrangement where you have a water flowing, pipe or water or any other liquid. And what we do is we insert something like a small straw, of course, like a metal piece, something like this. And then there is another piece is inserted like this. So what's going to happen here is when the water is flowing like this, let's say the water is flowing in this direction. Okay, this tube should be facing this water flow. As I told you, the water or liquids will have some pressure. Okay, so it's going to have some pressure at this point, which you are going to call it as A. Then there is going to be some pressure at this point, which is B. But you see here, the water is still flowing. Okay, whereas here the water is going to hit this pipe and then stop here. Okay, which means here the velocity is higher. Here the velocity is lower or almost zero. Which means to say that you know that pressure here should be low. The pressure here should be high according to your Bernoullis principle. So since the pressure here is low and pressure here is high, right? What will happen is there will be a height difference here because this is low pressure, which means the water level here will be lower. Whereas this is high pressure, which means this will be pushing the water more. So it's something like, you know, high pressure is kind of pushing this. Okay. Which means I can take this, I can measure this height difference between this level and this level using a simple scale or something. And I can tell easily what is the pressure differential. And then I can use the same principle which I used in the previous thing. So let's go through this. Energy at A is equal to energy at B. Energy at A is pressure at A plus half rho VA square plus is equal to PB half rho VB square, no doubt in it. Potential energy is not considered because same height. So which means both will get cancelled. I want to find the velocity, right? Half rho VA square. So PA goes on the other side. So PB minus PA. Why? Because we said this is higher and this is lower. So I'm making, you know, I'm trying to keep this as positive. Here it was the other way around. So if you see this, I assume that this is A and this is B, which means pressure here is higher. So PA minus PB is positive. So bring this on this side. Rho GH is a height difference. Half rho VA square. So VA is equal to root of 2G. Rho cancels. Okay. So the interesting thing here is there is no manometer liquid. So the liquid in the pipe itself is acting like a height difference liquid. Okay. So because of that, I can say that this row and this row are same. Here that was not the case. You see, this row and this row are different, which means you cannot cancel it. Whereas here you can cancel it so that you are getting VA is equal to root of 2GH. Okay. Very simple, nothing very difficult at all. If you understand the basic principle, energy A is equal to energy B. Okay. Modified Pitot tube is also exactly the same principle. Okay, I'm not going to go through it. Again, for your entrance exams, you will get this kind of problems also. Okay. But my job is to let you know that, okay, if you get a problem like that, you can always come here and take a look at it. Okay. So you see energy at A. So what the way this modified Pitot tube or Prandtl tube or air speed indicator. So there are so many different names for the same equipment. Maybe I can quickly, go through it so that you can study this yourself later. So what we do is we take a U-tube like this, and then you make a arrangement like this. You see this compartment and this compartment are different. So you see it's kind of separated like this. So when you put this inside a water, some liquid flowing pipe, something like this. Okay. So what we do is maybe I should improve this diagram over here to show that where the liquid is shown it. So again, let me repeat this. I told you this is like a separate compartment, okay, like a wall. So the liquid which is coming in here cannot go here. The liquid coming here cannot go here, right? So two different compartments. So this liquid will be pressing on this side of the manometer. This liquid will be pressing on top of this side of the manometer. Okay. So again, as we talked about earlier, the water is coming in here and then it's kind of stopped here because it cannot flow further. Whereas here, the water is still flowing. Okay, so if you make a small opening here, the water here is still flowing at a high speed. Okay, so here the pressure is going to be low. Here the pressure is going to be high. Everyone following what I'm saying? Even though this entire thing is filled up here, what happens here is this point at A and B. So we are talking about A and B. So here it's going to come and stop here. Here water keeps flowing, which means here the pressure is lower, here the pressure is higher. So you see the manometer liquid is shown like this. Why? Because high pressure here and lower pressure on this side. After that, it's the same story. If you understand how this works, nothing different here. So I'm going to leave it to you. Okay, do the same mathematics. If you are done so far, understood the earlier two cases, I'm sure you can understand it. Maybe I've used one more simple concept here, which is, if I draw a straight line here, you know that in any liquid, right, in any liquid surface, this pressure here and should be equal to pressure here. Did I make a mistake here? I think this must be Y. Or should I? Oh, okay. What I meant was this height is X and this height is X. And this line, if I draw it over here, this location is small x, this location is small y. So in a given liquid, right, if I draw a straight line, you know that the pressure at this point is equal to pressure at this point. So PB is what is pressing on top of this. Pressure due to the liquid column in X is also pressing X plus rho GH is this one. But then this height is pressed by this liquid, right? The liquid which is flowing here, the rho. Whereas this side it is the rho m. So you see here, this side I put this liquid. Okay, so the green color liquid which is passing through this, that is what is pressing on top of this mercury liquid. So that's why I used rho GH. But on this side, if you see who is pressing on top of this guy, pressure at A plus this X column, right? That will also contribute for some pressure. And then the rho GH. But here I told you rho m, you have to mention it as rho m mercury. Which means you can see that the pressure due to this liquid and this liquid column will cancel out. So that's why I kept it as X. So what is left is PB minus PA is equal to rho m minus rho GH. So now I can take this and put it over here. So that will give me this expression. Okay. And these are all expressions. Okay, you don't have to mug up anything over here if you know this basic principle. Okay, so that's for some entrance exam questions. Okay, when you face the questions, you should know that, okay, I can always come back and take a look at it and solve the problems. Okay, let's see. Okay, some of the other principles which are based on Bernoullis theorem, right? So this is nothing but a spray gun. Okay, for your, I'm sure all of us use this kind of things in our home, right? For spraying some liquids or some, what do you call it, like bathroom cleaners, and sometimes it will come in this shape, right? Even in your scent bottles, you have this pressing, right? When you press it, what you're actually doing is, okay, let's talk about this in detail. So when the air over here is pressed like this, it's going to rush out with high velocity. It is rushing out with high velocity. What happens? The pressure will decrease, and the pressure here decreases. What will happen? This liquid will start going up. Okay, of course, there should be some opening to the atmosphere. Only then the atmospheric pressure will press this. So this pressure will be lower than the atmospheric pressure, which means the pressure here will be pushing the liquid upwards. Okay, and that's what we are doing. You know, when you are drinking some liquid through straw, what are you actually doing? You are sucking it in, and what we are doing is we are creating a low pressure in our mouth, and we are creating a low pressure, the atmospheric pressure, right? So if you take a cup like this, if you have a straw like this, so you are creating a low pressure in your mouth here, which means this atmospheric pressure is higher than this pressure, which means this atmospheric pressure is pressing the liquid such that the straw will, the water will raise in the straw. Okay, water or juice or whatever you're drinking. Okay, so it's the same principle here. So suppose if you can try this in your home. Suppose if you completely lock this, right? So some to-go cups when you buy it in some fast food restaurants, right? They'll give you something, and here there'll be a small gap. Okay, why? Because atmospheric pressure should act on it. Suppose if you completely seal this without any gap at all, then try sucking this, you will not get any water. Why? Because atmospheric pressure is not acting on it. Okay, which means you will not be able to get the water liquid over here. Okay, so very simple, nothing very difficult. Anybody not following this? Everyone following this? Velocity, so take it down. Velocity is high. Pressure is low. So liquid rises. As I told you, it's not only the spray gun, even in your scent bottles, deodorants, everywhere, you know, you use the same principle. When you're pressing the knob or whatever you call it in the top, right? So you have something like this, and then you have something like this, and there is a hole here. So we press this. So when we press this, what we are actually doing is we are trying to rush the air through it. Okay, when the air is rushing through it, there will be a small straw inside this. So the liquid over here will be raised through this so that it can come out and it will be atomized through this. Okay, so it will mix up with the air coming in, and then it will be atomized, meaning it will be like, you know, very small particles. Okay, so that is one good example of Bernoullis theorem. Of course, the next example, airfoil experiment, we already talked about it, right? So I told you the airplane wings are nothing but airfoils. So the pressure, the air flows this way and then the air flows this way, right? So it is designed in such a way that this will be of longer path compared to this path, which means the air has to rush through this. So what happens here is this is high velocity, velocity higher, pressure lower. Here velocity is lower, pressure is high, which means it will create a pressure differential and it will push this up. So higher pressure will push the wing upwards, okay, or it's called airfoil. Okay, so nothing very difficult here. Okay, if you have been following all this Bernoullis theorem, this is a very simple concept. Magnus effect. So the next topic is, you know, this also given in the handbook. So Magnus effect It's a very interesting thing. You can try this, but you need to have a very tall building to try this. Let me see if I can find. Let me find some video.
I'm not able to see your screen, sir.
Yeah, just a sec. Just trying to find some good. Just trying to find the correct video. Okay, so let me see. Okay, so you can watch this later also. Okay, you can check out this backspin basketball price of dam. So what they are doing is they are standing on top of a dam, which is like 126 meters, very tall structure. So first they are dropping a basketball, and when it is dropped, it's just due to some air or wind, it's kind of falling. Let me play this one more time. You see, they are just dropping it, which means it's falling somewhere very close to the place where you dropped it, right? But now, suppose if you give a backspin, so you see what happens. The ball is kept, keeps on going. So let's watch it one more time. So that's a backspin. So you see, initially it's falling down vertically, and then it keeps moving in a horizontal direction. And sometimes in sports, in football and cricket and all, we use this kind of spin concepts to confuse the other person. You'll be thinking that it's going to fall vertically downwards, but actually it's falling in a different way. Okay. And interesting thing here is, the basketball works very well because it has some kind of a roughness, okay, rough surface. So imagine that the ball is falling down and the air is, flowing upwards, okay, because when the ball is falling down, the air is actually going the opposite direction. So what happens here is, so imagine that the ball is going this way, which means to say that the air It can be air or it can be any other fluid, but mostly we are doing our experiments in the air. So when the ball is going like this, right, the air flow is like this. But instead of dropping the ball straight, right, when you give a back spin, when you give a spin, as I told you, there must be some kind of a small roughness on the ball, only then this experiment will work. So what happens is when you have a small roughness, the ball just like a basketball. So the ball is given a spin. Let's assume that it is spinning this way, right? So the air flow, as I told you, it's flowing. So the air is flowing this way. Okay. And then initially the ball is given velocity this way along with the spin. Okay. Now carefully observe what happens here is the air molecules which are very closely attached to this ball, it will be trying to flow along with this ball. Okay. Whereas the air molecules which are attached on the lower side, right, which are very close to the basketball, it will try to go this way. You're unable to follow what I'm saying? Carefully look at the green arrows. Okay, there has been some textbook error in the NCERT textbook, so take these arrows correctly. So what happens is this blue and green are in the same direction, but look at this, the blue and green are in the opposite direction. So here the velocity of the air molecules will increase. Here the velocity of the air molecules will decrease. So which means the same concept. So here I can say the velocity increases. Here the velocity decreases. So when velocity increases, pressure decreases. Here pressure should increase. That means what did you do? You created a pressure differential, right? So that means what will happen is this is a high pressure, this is a low pressure, which means there will be a push this way. Or we can say the differential pressure, right, from higher pressure to the lower pressure. Which means to say that it's not only falling down vertically, it is also having a vertical. Okay. Maybe since this is the diagram given in the book, I tried to draw it, but there is some arrow error, so take it down properly. As I told you somewhere at the beginning, whenever possible, try to use some different colors. Okay, it's easy for you to understand things, particularly these kind of arrows. So in the case of dam experiment, which they did right now, what's happening here is, let's say this is a structure and you are standing here, you are dropping the ball. So when you're dropping the ball, it is kind of falling down vertically down. Okay. But if you do the same thing with the back spin, right? So listen carefully. The ball is having a back spin like this. Okay, which means when you're standing here, it should spin towards you. Okay. So according to this Bernoullis principle here, what did we say? The air molecules are going upwards like this. So the green one here, it will add up. Here this will cancel. So that means here the velocity is higher. So the pressure is lower. Here the velocity is lower. So the pressure is a little bigger. Here the velocity will cancel each other, right? You see the ball is going downwards. The blue lines are the air molecules which are rushing through upwards. But then because of the spin, this yellow lines will be spinning around. So the yellow is also the air molecules. Maybe I should have shown the green one. So the green one is also the air molecules, but those are the air molecules which are closely attached to the ball. Okay, very close to the ball. So here the velocity will decrease, which means the pressure will increase, which means you created a pressure differential, which means higher pressure to lower pressure, it will cause a push. That means due to the gravity, right? It is falling down this way. But because of this push, right? So initially it will be falling down something like this, and because as the Bernoullis principle comes into play, comes into picture, right? So what happens is, as the speed increases, only this effect will be more. Okay, initially the speed is very low, which means you see in the YouTube video itself, initially it will be falling down vertically. And after some time, only just before reaching the ground, right, the push is so high that it will be taking a path, something like this. Even the water, you can see that it's not a graphics or anything, it touches the water surface and then it keeps going like this. Okay, so that's a very beautiful video. So something which is thrown here, it keeps going all the way this way. Okay. So this effect is what is called Magnus Effect. So there are a lot of videos on YouTube. So try to take a look at it, Magnus Effect. Okay. So maybe I think, yeah, if I remember correctly, it was the name of a German scientist who explained this effect. That's why it's called Magnus Effect. Study something called Doppler effect, Magnus effect. Anybody not following this? Any questions? Okay, so we finished fluid dynamics. Okay, so we talked about equation of continuity, principle, Bernoullis theorem, and application of Bernoullis theorem in these 4 different situations. And then we talked about Bernoullis application in some other situations like airfoil spray gun, Magnus effect. Okay, so this is also interesting topic called viscosity. So you must have heard the word viscosity or viscous fluids. Okay, any idea what that means? What do you think in your general English? What do you mean by viscous? Viscous liquids, viscous fluids. No idea.
No idea, sir.
No idea. Okay, so if you are trying to pour water from a container, and if you are trying to pour honey from the bottle, right? Which one is easier? Which one is difficult?
Water.
Water is easier, right? Honey is difficult. Why? It is kind of sticky. So it will be sticking to the layers of the glass, and then within the honey itself, it will be sticking to each other. So you have to wait for a long time until the honey comes out. So if you carefully observe the way honey is pouring out, what will happen is, suppose if you take a container like this, suppose let's say I have a honey in this container. So suppose if you had some honey here, what will happen is, if you carefully observe, you will see that the top layer will be moving, but the bottom layer will be sticking to the glass. Okay, so the bottom layer sticks. The top layer tries to move, but still this does not allow it to fall very easily. Means the top layer flows slowly. Okay. So if you take water, this will be flowing out very quickly. Okay, why? Because there is not much of a stickiness between the water molecules. Whereas here there is a huge amount of stickiness. Okay, and not only stickiness, it's not only sticking with the same molecules, it is also sticking with the container, which is the glass. Right. So this stickiness, right, in general English we call it as sticking or stickiness. In physics or engineering we call it as viscosity. But stickiness is a qualitative term, right? I can say honey is much sticky compared to water. But compared to water, oil is more sticky, right? So that means I can say water is here, water, and then say oil, some oil, vegetable oil, something, and then honey. Okay. But that is a qualitative term. What do you mean by qualitative? We cannot put any numbers. Okay. But in engineering and physics, we like to put some numbers. Okay. So we have to know how do you compare different materials for different properties. So what we do here is somewhere else in the solids, right? We studied some concept called the top layer moving and the bottom layer not moving. Anybody remember what was that concept? Shear, very good. So that means the bottom layer is sticking, whereas excuse me, let me get some water. So something very similar to shear, right? Shear stress. The same kind of concepts can be applied over here. Okay. Of course, it's not exactly the same, but something similar. So the way we do this here is, if I take, so I hope I have given you a basic idea about what is viscosity, right? So let us talk about the small derivation over here. So suppose if you take, again, these diagrams are not properly given. Okay, I don't think there is any diagram for viscosity. So take it down properly. Maybe in the handbook I have given it. Suppose if you take a wooden plate or some plate over here, and if you fill the gap between here with water. Yeah, of course, I'm just exaggerating the size so that it's easy for us to imagine what's happening. And let's say the same gap here is filled with oil, sorry, honey. Suppose if I'm applying a force on top of this, right? Like a shear force. You see, I'm not pressing this, I'm shearing this. Okay, so that's what is your shear force. So moving this is going to be much easier. Moving this is going to be much difficult. Okay, so based on this, we have some quantification for this viscosity, right? So what is the area, the cross-section area of the plate? So you have a cross-section area here, cross-section area here. Sorry, not cross-section area, the area on the top. Okay. Again, these things are 3 dimensions, so you have to understand if I say area, you should not be thinking this area, it's the area on the top. So the force that is required to push this, right? Will be proportional to area, and then it will also be proportional to change in velocity, dv by dx, with the height. This term might be slightly confusing, so listen carefully. So as I told you here, the velocity of the top layer and the velocity in the bottom layer. So if you consider water, for example, right, the velocity on the top layer and the velocity in the bottom layer will be almost the same. So the change in difference in velocity will be less. Whereas in the case of honey, Here the velocity will be higher. Here it's almost sticking, which means it's totally zero, right? Almost zero. That means here the velocity and this is kind of zero. So this height difference for a given height difference, right? What is the velocity difference? And that is what this represents. To take it down properly, velocity gradient. So with respect, so this is your x, this is your v. Okay, so what is the v1 and v2? So suppose if I say this is v1, this is v2. So dv is v2 minus v1 divided by this height x. That's what we in calculus. This is what this is how we represent this dv by dx, velocity gradient. Whenever we have proportionality, what do? We bring in a proportionality constant. So that means what we say is it's not only dependent upon the area and the dv by dx, it is also dependent upon the viscosity, coefficient of viscosity. In other words, if that is confusing, right? As I always say, most of the time, if you understand this equation, you will understand the proportionality constant and you will understand how the quantities are given. For example, material properties, medium properties. Even in your 12th standard, you are going to get a lot of things like this. So suppose if I want to understand what is this eta further, right? So eta is your coefficient of viscosity. So F is equal to eta A dV by dx. So if I want to understand what is eta, I can write this as A comes on the side, so force by area divided by dV by dx. What is force by area? It's shear stress. This will be called as shear strain, okay, but it's rate of change of strain. The handbook I not given this properly, so take it down properly. So it's actually shear stress and shear strain. So this I'm going to call it as shear strain rate. So it's not just shear strain, it's shear strain rate. Remember, this is not shear modulus, it's a liquid quantity. So with respect to time, we have to. How did I call this as shear strain rate? Let's see, dV by dx. Okay, what is dV? Length by time. Okay, so that means dx by dt divided by, actually this is in this direction, right? So I'm going to call this as L. Bit confusing diagram, so take it down properly. So as I told you, this is your height x. Okay, how much this has moved compared to this velocity and this velocity, how much length it has moved more. Right? This distance, this difference, it's called as L. That means this movement is in this direction. This x is different, this L is different. So this is not dx by dt. So it's dl by dt divided by dx. So what is dl by dx? So if you go back to your solids chapter, you will see that what is the change in this direction divided by this, that is nothing but your shear strain. That divided by dt. So I'm rearranging this to make it easy for you to understand. So dl by dx is nothing but shear strain. Divide by time will give me shear strain rate. So in other words, we are having two different ways of understanding coefficient of viscosity. One is from this, I think this is called Newton's formula. So from the proportionality you can derive this, and from there you can derive this one, dV by dx. So coefficient of viscosity is shear stress by shear strain rate. Okay, I talked about the dimensions in the handbook, so you can go through this. Maybe let me say this one more time. So what I was trying to say here was, when you have a bigger plate area, I need to apply more force. When you are applying, when your velocity gradient is smaller, your force is less. But when the velocity gradient is higher, then the force will be more. But then that alone does not determine the force which you are applying. It also depends upon the material. So, for example, water, the force which you apply will be very less. Whereas in the case of honey, the force which you apply to cause the same velocity gradient will be much higher. Okay, so only if you apply a huge amount of force, you will be able to cause the same velocity gradient. Okay, so that needs a little bit of thinking. So think about it, make some notes, and then think about it. I'm sure you will be able to follow it. Okay, this is very simple. The next topic is called laminar flow and turbulent flow. So as the name suggests, turbulent means very fast, okay, very mixing kind of thing. So if you go to the tab, okay, go to your tab. The tab looks something like this. Okay, you open it very slowly. So what happens? The water is coming very nicely. So at every point, right? Again, as I told you some time back, one thing is physically you have to understand it, and another thing is understanding it in the engineering perspective or from a physics perspective. So if you open it very little, you will see that the water is coming out very slowly, okay, and it will be very nice, and it will be nice to see. And suppose if I take a ink pen and then if I put it over here, put the nib over here, right? So what you will see is, you will see that, or maybe if I draw it properly here. So suppose if this is a water flowing, and suppose if I keep the nib over here. So what you will see is, you will nicely see that this line alone will be having a different color from the pen. Okay, so it will be taking away the ink. Water will be sucking in the, or taking the nib color from here. Okay, so here and all, it doesn't have any effect. So the water keeps flowing in this direction. Here also it keeps flowing. But here alone, you will see nicely, the color changes to blue or something, depending upon the ink color. Okay. So what we say is this kind of flow where it is not mixing up. So as you open the tap, what happens? The water will just start rushing through, so it will not be having a proper path. So you see there'll be a lot of eddies, and it's kind of turbulent flow. Okay, so the molecules will be coming here, the molecules will be coming here. So everywhere it is kind of moving. So this kind of flow we call it as turbulent flow. This is what is called laminar flow. Okay. We have a simple way of, again, as I told you, what we understand is one thing, but in engineering physics, we always want a quantification, right? How do I know that, okay, this is laminar and this is turbulent? We need some kind of numbers. So what we do is, again, this is basics for your fluid mechanics in your college. Okay. So we'll study more about this in your college if you are going to take mechanical, aeronautical, automobile engineering. So there is something called Reynolds number. So it's given as rho Vd by theta. Again, we don't have any derivations right now for this. Okay. So the classification here is Reynolds number is equal to 1000. Of course, there will always be some, different books will give slightly different numbers. So let us not argue on that. Okay, whatever your book is giving, maybe we can follow that. Reynolds number 1000 means laminar streamline flow. Here it is, if it is more than 2000, right, we call it as turbulent flow. If it's between 1000 to 2000, it's more like a mixed flow, unstable. Okay. You cannot call it as laminar, you cannot call it as turbulent, so it's somewhere. Again, rho is density, v is the velocity, d is the diameter of the pipe, eta is the viscosity. Okay, so that's why this is coming under viscosity chapter. Any questions? Anybody not following? Okay, so let's see. One small topic for today, and then we'll wind up for today. So this, we have this experiment in our lab. So what we do is, you take a burette. Okay, in your chemistry lab, you must have seen some burette. If you're not gone to your chemistry lab, then it's cannot do anything about it. Okay, so here we have a burette like this. So it's nothing but a small, or like 1 meter long tube, glass tube. So what we do is we fill this up with glycerin. In medical shops, you can get glycerin. So the glycerin is a very viscous liquid. Okay, it will be very sticky. And then what we do is we drop some steel balls of different sizes. So when the steel ball is dropped, what you will see is very interestingly, initially it will be going fast, but then after a while, what happens is the speed will not be increasing. The speed will be going at a constant speed. Okay. So that speed, right, the constant speed, when it is falling down with a constant speed, we call it by a special name called terminal velocity. Have you heard terminal velocity anywhere else? I'm sure you have heard somewhere. Where did you hear? Nobody remembers terminal velocity? That's very sad. In parachute problems, we talked about it, right? So go back and check your chapter 5 notes. So initially the speed increases, and then after a while the speed comes to a constant value. And that is what is called terminal velocity. Terminal means it's coming to a stop. I mean, it's not coming to a stop. The velocity is coming to a stop. So velocity is reaching its maximum value. So in this kind of situations, right, we are interested in finding this terminal velocity. So what we do is a simple derivation, nothing very difficult here. So when the steel ball is falling through the fluid, you know that the gravity is acting downwards. You know that there is something called viscous drag. What do you mean by that? When you are going in a two-wheeler, right? So you face the air, right? So you have to go through the air. So if there was no air, it's much easier for you to flow. Of course, you'll not be able to breathe. But then, going through the air at a high speed, what happens is there is a lot of air resistance, and that is what is called drag force. So whenever an object is going through a fluid, like water or air or some other liquid, there will be some viscous drag force. Okay. Then there is something called upward thrust force, which we call as buoyancy force. So according to your most important formula in mechanics, right? Sigma F is equal to ma. If I say that it is coming to a constant speed, right? Acceleration becomes 0. Constant speed. So that means I can say this, you can take it as, it doesn't matter. I can write FB plus FB minus FG is equal to 0. Drag force, whenever there is a steel ball or a spherical ball falling through a liquid, there is a standard formula called Stokes formula. So it's given as 6 pi eta AV. So take it down. Right now we don't have this derivation. Okay. So we just have to remember this. Eta stands for the viscosity of.
This is given in the text.
Yeah, it is given in the textbook. But this derivation is not there. I mean, the drag force, how you got this formula, that is not there. Is that right?
Yes, sir.
So buoyancy force, we already talked about it. What did we say? Upward thrust force is equal to weight of the liquid displaced. Okay. So weight of the liquid displaced is nothing but ml into g. Gravity is nothing but mg. Okay, here I'm going to put a plus. This minus goes to the other side, so it will be m into g. This m stands for the mass of the steel ball. This m stands for the liquid displaced by the steel ball. Mass can be written as rho L into V. Rho of the object, V of the object. Okay, you say again, capital V means volume, small v means velocity. You see, if I put 1 liter volume, if I put 1 liter volume of a steel ball, it will be displacing 1 liter of water, right? If I drop a smaller steel ball, it will be displacing less water. So that means the volume of the object is equal to the volume of the liquid displaced because it is completely submerged. But then the density is different. So density of the liquid is different from the density of the object. So after that, it is very simple. As I told you, this V is the terminal velocity. This A is nothing but the radius of the ball. Okay, so this is called Stokes formula. Drag force of a spherical object going through a liquid can be directly taken as 6 pi eta AV. So take this on the other side. 6 pi eta AV is equal to, this comes on the side, so it will be rho naught minus rho L into V naught into G. Capital V stands for volume. The handbook I given it as rho and sigma, but I don't like it now, so maybe I should change it in the handbook also. Okay, because very often the confusion will come as which one is what, which one is density of liquid and which one is density of object. Instead, if you write it as rho naught or rho L, it will make it clear. So as far as possible, we should try to avoid some ambiguities or confusions. So let's use rho naught and rho L. Okay, so correct it in your handbook also. So after that, it is very simple mathematics. So as I always say, the first part is your physics. Okay. And after that, it is simple mathematics. If you're studying your mathematics properly, I'm sure you can do it. Volume of the object is nothing but 4 by 3 pi r cube, right? Four by 3 pi r cube. R cube is a cube, radius of the ball. A cancels, a square, pi cancels. 6 and 4 cancels, 3 and 2. This 3 comes on the side, it will become 9. So Vt, we call this as terminal velocity. Eta comes on the side, so 2 by 9. Eta also goes to the bottom. A square into G, then rho naught minus rho L. As I always say, don't try to remember the final formula. Okay. So if you are trying to remember the final formula, that's not the proper way to study physics. You should remember the underlying principle. What is the underlying principle? Weight is acting downwards, buoyancy force upward, thrust force is acting upwards, drag force is acting upwards. Why do you think the drag force is acting upwards? Because when you are going in a two-wheeler, right? I'm sure all of you experience this. So somebody is going in a two-wheeler this way, which means the air resistance is this way, right? So air is blowing on your face this way. But suppose if you turn this way and if you are going this way, and now the air is blowing on your face this way. Okay, so it doesn't matter which way the wind is blowing. Of course, the wind will have a different effect. Okay, right now we are not talking about wind effect. We are talking about the standstill air. So even if it's a standstill air, when you are going in a particular direction, the air resistance is always opposite, something like a friction. So similarly, what happens is when the ball is falling down, the drag force is acting upwards, opposite direction. That's all.
You can scroll a little bit
Yeah. So very simple derivation. Only for derivation you need to understand this. For your numericals, I would say if you remember this part, right, you can easily do the numericals. Okay. Don't waste your time trying to mug up these final formulas. Okay, so it's already late, 8:50, so I'm going to stop here. So it's already 3 pages completed, 3 main topics completed: fluid statics, fluid dynamics, and viscosity. Right, this is an important derivation which we saw today. This one, terminal velocity of a sphere falling through a viscous liquid. Okay. So next class we'll complete the surface tension. Okay, so it's slightly lengthy chapter because you have 4 different main topics. So start studying now itself. Don't wait for me to complete the chapter. Okay, if you have any doubts, stay back. Otherwise, you are free to go. Thanks. Bye.
Thank you, sir.
Thank you, sir.